Hello again. This is Math 2115 coming to you from the College of DuPage. And the title of this lecture is Sequential Circuits in Finite State Machines, or Finite State Automata. As always, please be an attentive learner as you watch this video. Previously, we discussed things called combinatorial or combinational circuits where the output was completely determined by the input. Now, they are very important in computer design, particularly hardware, but in software, equally important are things called sequential circuits. In sequential circuits, one cannot predict the output corresponding to a particular input unless one also knows something about the prior history of the circuit, or more technically, unless one knows something about the state of the circuit was in before receiving the input. The behavior of this sequential circuit function is not only an input to the circuit, but also the state the circuit was in when the input is received. A computer memory circuit is a type of sequential circuit. So, a finite state automaton, and that's the singular of automata, is an idealized machine which embodies the essential elements of a sequential circuit. And so an example would be dialing an 800 number. If you dial 1-800, that puts the circuit in a state of readiness to receive the final 7 digits of a toll call. But if you just start dialing this, that leads to a state of expectation for 4 more digits because it's a local call. Vending machines operate similarly, and we're going to look at a vending machine example here. Just knowing what you put a quarter into a vending machine is not enough to predict what the behavior of the machine will be. You also have to know if the machine is already in a different state. For example, if 75 cents has already been deposited, you might get a beverage or a candy. But if the quarter was the first coin, you'd get nothing at all. So here's an example of simple vending machine. So the states are: you could have nothing deposited, you can have a quarter deposited, 50 cents deposited, 75 cents deposited, or one or more, $1 or more deposited. And what would happen then is that these are the states that you would flow as you would go different places. For example, the machine accepts quarters and half dollars only and does not give change. As soon as the amount deposited exceeds $1, the machine releases a bottle of juice, and the next coin deposited starts the process again. So you can see what happens. You put in a quarter, and then you can put in a half dollar. Up to 75 cents, you can put in either a quarter or a half dollar, and you get down here. And this is a special thing because this releases the juice. Okay, so those are states that you can have. You could also design a machine so it gives change as well. So each circle, here this is recreated, and you can also, in addition to drawing a picture of this, you can also draw a next state table, as you see down here. Now, the initial state is indicated with an arrow, and here it also is indicated by an arrow. So that's where you start with this machine diagram, and then these are the different states. And this is a state that is a final state because something important happens there. So this is called an accepting state, and that's the reason we put a double circle around it. So key symbols then are certainly the arrows, the annotations, but this is the starting state, and this double circle indicates that that is an accepting state. So observe the vending machine can be thought of having a little bit of a memory. It remembers how much money has been deposited within limits, and that is because it's a finite thing and refers to that state that it's in. Now that's a very powerful thing, and that's a very most important thing to remember about finite state automata are digital computers. Each computer consists of several subsystems: input, processor, and output. A processor is a CPU in a finite number of memory locations. So you see it does have memory. At a time, the state of the processor is determined by the locations and values of all the bits stored within the memory. And then it's also acts on the input. So a computer has n different locations for storing bits. And each of them can be, let's say, a 0 or 1, and so this is 2 to the n different states. Now, n is in many billions, so this is enormous, but it is finite. And so that makes this very useful to study this, to provide help. And this is actually what is a key component of compiler design. And the basic theory of automata was developed to answer very theoretical questions about the foundation of mathematics that Hilbert posed in one of his very famous lectures. And Turing did great work in addition to cracking codes during World War II. And so you see these names feeling very prominently in the study of this subject. So let's then look at now, generalizing the vending machine, the definition of a finite state automata. And so this is 5 objects. It is an input alphabet, symbols you can use as inputs, a set of states, the initial state, S0, designated states that are called accepting states. For example, in a more complicated vending machine, you might pick apple juice or orange juice, and so those could be different accepting states. And you also have a next state function that operates. It takes your state and your input and maps it to the states. So this is how you move from one state to another. So these are the 5 things that make a finite state automata, or a finite state machine. So we can talk about transition diagrams, and we can also talk about transition tables. So here's a finite state automaton, A, defined by this transition diagram that you see here. And we can ask questions about what are the states, input symbols, input states, accepting states, and calculating the transition function. And also you can be asked to construct a annotated next state table given the diagram. And so when you look at this, you can see that the states are 0, S1, S0, S1, and S2. The input symbols are 0 and 1, because that's what's on all of these arrows. The state of the initial state is S0, because that's where you have an unlabeled arrow going into. The only accepting state is where you have double circle around. And the transition diagram says if you're in S1 and you get a 1, so if you're in S1 and the input is a 1, you go to S2. And if you wanted to build an annotated next state diagram, you do this. Notice you put the initial state, the final state, and then you show where the transitions happen. And so this represents that. Sometimes you can start with a table and draw a diagram. And so here's a different one. So we have what are the states? And the states here are U, V, Y, and S. The input symbols are A, B, and C this time. And the initial state is U, because that's where this arrow is. There are 2 accepting states. It can be V or Z in this case. If you're at U and you get C, you get Y. Because if you're at U and you get input C, you go to state Y. You can see that from that. And then you can draw these transition diagrams. Here is a very elaborate one, but then since B and C have the same thing, you could simplify that drawing to represent it this way. And when you have a compiler, the compilers are based on languages. And so we talk about languages that are accepted by an automaton. And there can be more than one. In fact, suppose a string of input signals is fed into the finite state automata in a sequence. At the end of the process, each successive input symbol has changed the state of the thing, the automaton, and the automaton ends up in a certain state. But that state may either be an accepting state or a non-accepting state. In this way, the action of a finite state separates the set of all inputs into two substrings, those that send it into an accepting state and those that are not accepted. And so those strings that send it into an accepting state are accepted by the automaton. And that is an important thing. That's basically a key function in a compiler. So let A be a finite state automaton with a set of input symbols I. I star is the set of all strings over I, and W is the string in I star. If W is accepted by A, if and only if A goes to an accepting state when the input signals are input into A in the sequence from left to right, starting when A is in its initial state. The language accepted by A, L of A, is the set of all strings that are accepted by A. Again, a critical function in a compiler. Okay, so we can ask the many questions. Find the language accepted by this automaton. Okay, so if we look at this, what we're trying to do is say what goes to the accepting states. Okay, so let's answer those questions. To what state does A go to if the symbols in the following string are input, starting from the initial state to the final state? Which of the strings are go to accepting state? What is the language that's accepted, and is there a regular expression that defines this language? So there is our picture. And the picture is recreated up here smaller, but what we see is that each of these inputs go to S2, S0, S1, and S2. Now you want to work through this example and understand that. Of which of the strings send it to an accepting state? Well, only two of them do. So this one and this one. And you notice that they both end in 0, 1. And so when you talk about what really is the coding of that, you can say, well, it's anything that ends in, so this is zeros or ones, the whole set of those, but it ends in 0 or 1, it will take it into that. And here's a little bit of a proof of what is that language. A finite state automata with multiple accepting states can have output devices attached to each one, so it can classify input strings in a variety of different categories, one for each accepting state. You could think about this as being the vending machine that would dispense apple juice or orange juice. More generally, however, this is how finite state automata are used in a lexical scanner component of a computer compiler to group the symbols from a stream of input characters into identifiers, keywords, and so forth. Now suppose a finite state automata is in one of its states, not necessarily the initial state, and a string of input symbols is sped into it in a sequence. To what state will it eventually go? And that comes from a thing called the eventual state function. And you see this is similar to the next state function, but we're going to use n star to do this. So let A be a finite state automata with a set of input symbols I, sets of states S, and the next state function is this. It goes from S cross I to S. But now we're looking at I star, and this is the set of all strings. And the eventual state says this is S cross now I star. So to S, and this is for any state S and any input string W. N star of SW is the state to which A goes if the symbols of W are input into A in sequence, starting when A is in the state S, not necessarily the first state. So we're considering the example that we just talked about, and here we're going to go through and talk about the event. So we'll start at S1, and we'll put this as input stream, and we see that goes to S1. So this is where it goes. Now S1 is not one of these eventual states, so this would not be accepted. So something is accepted by A if the answer to this is an accepting state, and vice versa. And we can define the language associated with A as a set of W's that do go into an accepting state. So these are the symbols that will cause you to go into a state where the machine will take action. Now we can actually think about designing a finite state automaton also. So here we're talking about designing a finite state automaton that accepts strings of integers that are zeros and one, but only those where the number of ones is divisible by 3. And we're asked to design a automaton A that accepts those strings, and then we're subsequently asked if a regular expression does in fact define that. And what can be seen, and this is the goal, is to define such a thing. And so what we are going to do is we're going to go through and talk about that. And so we end up with this being the solution. And you should check and make sure that this actually does what you want it to do. Now, and the answer for the regular expression is that it will look like this. So you see there is a relationship between the finite state automata and a regular expression that defines that set, the language. And there are other examples. Here's another example where we talk about a finite state automata that accepts the string of all zeros and ones, but you have to contain only exactly one. Here is the set of, here's the transition diagram that will satisfy that. You should verify that. And it's a regular expression that defines that set. And there is. It is 0 star 1 0 star. So you're kind of saying, gee, it looks like there's a relationship between regular expressions and in fact Kleini's theorem, and in fact this is kind of an if and only if, and the proofs are up by induction on in, and to tell you the truth, they're really quite involved. But any language that is accepted by a finite state automaton, there is a regular expression that defines the same language. And given any language defined by regular expression, you can make a finite state automaton that accepts that same language. So there is a strong equivalence here. Again, the proof is pretty complicated, and it's induction by in. Now, these are called regular language, but we also talked about that. There's another classification of languages that are context-free, and these are called, you have a context, these are context-free languages, and those are broader. And here is a little existence proof that there is a language that is not regular. And it's this example, and you might notice that it uses the counting pigeonhole principle that we've talked about before, and it's a proof by contradiction. And this would be a good proof to blow up and go through the proof in detail. Again, it requires quite a bit of thought. So in closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.